Hello, I'm here to demonstrate the sensor subsystem for the smart alarm clock team. I'm Nicholas Hirsch, studying electrical engineering, hoping to graduate this semester. So basically what I've got right now is all these sensors hooked up to the ESP32 microcontroller. I know that the wiring is a little janky, but we're trying to make do with the best we've got right now. So as for the code, I can walk quickly through it. It's just basically using a bunch of the libraries that Adafruit provided. The only thing is that the CO sensor didn't come in time, so I wasn't able to add the analog part to it. But just running through it, these are the libraries I'm using, and it was pretty straightforward, just implementing all the code to get the sensor set up and get the right I2C address. And through this code, it pretty much just reads the data, and then I have the data being fed into a variable to be stored later on the SD card once we've got those systems connected. But for now, I'm just using these variables to kind of put the readings into different levels, like I said during the manager meeting. So yeah, here I'll upload the code really quickly again to the ESP32 to verify that it's working correctly. So here, uploading the code, pulling up the serial monitor, and here, there it goes. So it runs through a few tests and then verifies that everything's connected, and then it shows the readings of the sensors. As you can see, I'm going to quickly breathe onto the CO2 sensor to show how the readings change to verify its correctness. All right, and as you can see, the CO2 levels rose as I was breathing on it, and it put it into the red category as the levels were quite high, as I was just pretty much breathing right onto it. Now I'm going to cover the light sensor on the lux sensor, and you can see those readings change as well. As you can see, I'm covering it, and the levels are pretty much now 0 compared to what they were before. And as for the temperature sensor, I'm just going to hold my hand on it and hope it warms up in a reasonable amount of time, just to show how that's working. Yes, as you can see, the temperature rose quite drastically, and the humidity also went up quite a bit. Just verifying that all sensors are reading correctly and that the data is being stored, which can be used further in the project. All right, you guys have a good day.
Hi, my name is June, and I'll be demonstrating the clock and display subsystem. The display is connected to the microcontroller using SPI protocol, and it displays the current time, temperature, humidity, carbon oxide and carbon dioxide, and the light data. Currently, it's using arbitrary test data as other subsystems have not been connected with the clock and display subsystem. The time is first set up into the system clock in the ESP32. Then it uses a timer-based interrupt of 50 milliseconds to check whether a second has passed or not to update the time on the display. Instead of using physical button to cycle through the different data, I decided to put all the sensor data into one screen. I've not implemented the alarm or snooze functions to the clock yet, but I plan to add that in as soon as possible. Thank you for watching.
This is the Bluetooth subsystem. Here I have an ESP32 on a breadboard to simulate it. The potentiometer here is to simulate the sensor subsystem. I have a speaker and battery to simulate the power and speaker subsystem, and ESP32 itself to simulate the clock subsystem. I will now go over some of the specifications for my subsystem. They are synchronize the clock time with the phone, set alarm sounds over Bluetooth, set alarm times over Bluetooth, and transfer sensor data and display it on the app. Alright, let's synchronize the time with our phone to the ESP32. First connect to the smart clock. We're now connected. Hit sync time. It is currently 2:53 and it is 2:53 on the ESP32. Let's now set an alarm time over the ESP32. It's 2:53. Let's set it to 2:55. and we hit set alarm. So now we can see the alarm is set, and now we wait. Okay, it's about to hit 2:55, and it will play a sine wave as our alarm, and we can change the alarm sound. And it'll play for about a minute. Okay, so I was not able to receive data on the app from the ESP32. However, the ESP32 is sending the messages, the app's just not receiving it. To demonstrate this, I have a potentiometer here. Change the values sent to the serial monitor. And here we have another app that allows us to monitor Bluetooth messages. And here we can see that the same message is being sent from the ESP32. So the ESP32 is sending messages, it's just my app is not working.
I'm Leon Petrulio. I'm a senior in electrical engineering and I'm part of the Smart Alarm Clock team. And this is a brief introduction to my power subsystem demo. So we will be accessing power from the wall, which will then be converted to DC power through a wall-mounted AC adapter, which will supply 12 volts of DC power. And this will then be accessed by two different circuits, both of which revolve around a low dropout regulator, one of which will step down the 12 volts to 3.3 volts for the components which require such voltage. And then the other circuit will step down the 12 volts to 5 volts for the components which require that voltage. So we'll take a look at my circuit to see if it does such. As you can see right here, we have our wall-mounted AC adapter, which is then connected to a barrel jack port, as seen on the right. And currently the oscilloscope is connected to the output of that as well as the ground. And we can see an average voltage reading of hovering just around 12 volts. And to use the cursors, just to solidify it, right in the middle of that yellow line is just about 12 volts. And then on the left side right here, we have our 3.3 volt portion of the circuit. And on the right side, we have our 5 volt portion of the circuit. So I will connect the oscilloscope to the 3.3 volt portion of the circuit. Go back up to the oscilloscope, auto scale it, and as you can see, the average reading is just about a little lower than 3.3, although for our purposes that should be fine. And then using the cursors, just to clarify, bring it up right about to the middle of it, we're sitting at just around 3.3 volts, slightly below it. And then I will then connect the oscilloscope to the 5 volt portion of the circuit. Auto scale this briefly. And as you can see, the average voltage is being read as just about 5 volts, slightly under. Use the cursor just to reinforce it. Sits just around 5 volts. And this is a simplified block diagram of my sound subsystem demo. So we have an audio signal, which is going to be passed into a mono audio amplifier. We just have one speaker, so a stereo audio amplifier is not needed. Mono is fine. And then this is going to drive a 4 ohm, 3 watt speaker. So let's see if we get sound from the speaker. So I'm getting audio from the computer through an auxiliary cable, which is connected to an auxiliary port on the circuit. And then we have our audio amplifier, which its output is connected to our speaker. So I have a song queued up, so I'll play it. So it sounds good. It's reasonably loud and the quality is pretty solid.